The focus of this module of lectures in the course is to cover contemporary topics that are relevant to classical tasks in computer vision. Going with this theme, we will now talk about how transformers have been used for the next classical task in computer vision, which is image segmentation. A few weeks ago, you may recall that we spoke about methods for image segmentation. Image segmentation seeks to partition images into different image segments, each of which are associated with certain object classes. If you recall, we spoke about CNN models like SegNets, DeepLab, MaskRCNN, and so on, which did quite well on semantic segmentation and related tasks. But expectedly, since the disruption of transformers, they have been used for semantic segmentation too. What we'll try to focus on in this lecture is talk about a few such architectures that use transformers for semantic segmentation, and we'll focus on one of the most recent methods, which is segment anything, in more detail because of its significant wide use. In the previous lecture, we spoke about object detection and we spoke about the DETR framework for object detection. A natural follow-up to ask is, can we go from end-to-end object detection to end-to-end semantic segmentation, which led to one of the earliest papers on transformer-based visual segmentation called SETR. This was published in CVPR of 2021. We are not going to go into the detail of each of these architectures. We will very briefly cover a few of them before we go into segment anything. But just to quickly revisit, you see the overall architecture of the SETR module here. It has the standard transformer layers. It replaces convolution layer based encoders with a pure transformer, which gradually reduces spatial resolution over the different transformer blocks. You can see here that there are image patches. These image patches go through a linear projection, after which they are appended with a positional encoding, and then they go into the transformer encoder. And then there is a decoder where they have two variants, one called SETR PUP, which is progressive upsampling, which is what you see on top here, and a second one called SETR MLA, which stands for multi-level aggregation. You can see here that both of these strategies were used in the decoder because when you perform semantic segmentation, you need a classification at the level of each pixel. That was the reason they needed this upsampling, very similar to how we saw such things with, say, the SegNet architecture when we talked about it earlier for semantic segmentation. A subsequent method was the MaskFormer, published in NeurIPS of 2021, where they used a hierarchical transformer encoder for feature extraction. You can see the encoder part of the architecture here, followed by a lightweight MLP decoder for predicting the final mask. So they used a patch size of 4x4 instead of 16x16 in standard VITs. They followed a patch merging process, what you see here with the H by 4 and H by 8s and H by 16s, which should remind you of the Swin transformer. Their patch merging process or the hierarchical transformer encoder had a very similar strategy as the Swin transformer, and they also proposed a position encoding free design in their entire architecture. You can see here that there are no position encodings anywhere specified. Each transformer block has the standard self-attention, feed-forward neural network, and then the overlap patch merging operation before the outputs are fed into the next transformer encoder block. And finally, there is an MLP layer where you also upsample before you send it to a lightweight decoder which classifies every pixel. Subsequently came an important improvement called the MaskFormer, which came in NeurIPS 2021-2, but they had an interesting premise of how to go about semantic segmentation using transformers. One thing that should be clear by now is the use of transformer using self-attention layers and MLP layers inside the transformer block are fairly the same as the original transformer or the vision transformer or the DETR. The challenge comes in how are you going to address a given task using the transformer architecture. In DETR, we saw that the idea of introducing object queries at the decoder was critical to translate the transformer architecture to a detection task where there could be multiple bounding boxes with different objects in the image. So the question then arises, how do you make this happen for semantic segmentation in an efficient manner? MaskFormer had an interesting strategy which has been taken up by many other methods since their proposition. So let's see this in some detail. So this is the figure from the paper where given an image, they send it through a standard backbone, a CNN backbone, a VIT backbone, through which they get image features which are fed into the transformer decoder, but the image features are also fed into a pixel decoder which has a few upsampling layers before it goes to the same size as the original image. So the job of the pixel decoder is to keep upsampling the image features until you get the same size as your original input image. Now the transformer decoder, similar to DETR, takes in n queries which are then converted to n output embeddings of the decoder. What do these n queries correspond to? These n queries correspond to n masks that we want to capture in an image. Remember, the job of semantic segmentation is to output segment masks inside the image. So these are the queries for the masks, and the output decoder encodings are fed into an MLP which gives two outputs. On one hand, it predicts the class label for each of those mask queries. You could assume that this now corresponds to which class does each mask belong to. Does it belong to a car, a pedestrian, a tree, a pavement, so on and so forth. The output of the MLP also gets converted to n different mask embeddings of dimension C epsilon cross n. So each of those n mask embeddings have a C epsilon dimension. Now you see here that the output of the pixel encoder also led to a C epsilon cross h cross w dimension. Remember, it was supposed to be the size of the original image, which is h cross w, and each of those pixel embeddings are of dimension C epsilon. Now they propose taking a dot product between this C epsilon cross n and these per pixel embeddings C epsilon cross h cross w, and what you're left with is n cross h cross w tensor. So you do your dot product on the C epsilon dimension and you are left with n cross h cross w. What does this give you? This gives you n mask predictions, each of size h cross w, which is the image size. You could now visualize these mask predictions as a binary mask of the entire image size, where you have white corresponding to the object and black all around in the image. That's what these binary masks are. So, and the overall network is trained using a classification loss here and a binary mask loss here, which match the ground truth masks given in the data set. And the final segmentation is obtained by combining these two to give a singular output, which is k cross h cross w, which gives you k masks on your h cross w image, where you drop all the masks which may have no object in it or phi or an empty set. This approach of MaskFormer to adapt a transformer to the task of semantic segmentation has also been followed by other methods. It was quickly followed by another paper called MaskFormer, where the same authors extended MaskFormer as a universal architecture to perform all segmentation tasks, including panoptic, instance, and semantic segmentation. Please go back and see the earlier lectures on semantic segmentation to understand the difference between panoptic, instance, and semantic. In MaskFormer, the architecture consisted of a backbone feature extractor similar to MaskFormer, a pixel decoder similar to MaskFormer, and a transformer decoder similar to MaskFormer again. They introduce a masked attention operator which restricts the cross attention to the foreground region of the predicted mask and then extracts the localized features. That's the main contribution of MaskFormer compared to MaskFormer. We will not get into more details at this time. You're encouraged to go see the paper for more details. But one limitation of this approach was that this needs to be trained separately for each task, which is a common limitation of any method that says that it's a universal architecture for all kinds of segmentation tasks. Since these methods, other methods such as the segmenter, pyramid vision transformer, dense prediction transformer, HRFormer have all been proposed for the same task of semantic segmentation using the transformer architecture. As you can see, there have been different methods and each of them vary slightly in how they use different components like multiscale, attention, the prediction approach to getting the task, and so on and so forth to get different methods. Instead of focusing on all of these methods, we are instead going to focus the rest of this lecture on the most recent method called segment anything model, or popularly called SAM, primarily because this is the default model for segmentation today, has shown tremendous performance on various set of tasks related to segmentation. Let's get into SAM at this point. SAM is considered to be the first foundation model for image segmentation. What is a foundation model? A foundation model is a model trained on broad data that can be used for different tasks with minimal fine-tuning. GPT series of models or BERT series of models in NLP were foundation models. Similarly, SAM is a foundation model for vision tasks, especially segmentation kind of tasks. Its broad idea is that it's a promptable model. You may have heard of prompting LLMs or large language models like ChatGPT. Similar to that, Segment Anything uses the strategy of prompting the architecture with some additional input. What this additional input could be, we will see soon. And the model is pre-trained on a very broad data set using a task that enables powerful downstream generalization. That's the premise of SAM. So the task that they choose to train the model is promptable segmentation, where in addition to the image, you can also have other prompts that you give as input to your transformer. What kind of prompts can you give? You can give a point in the image as a prompt. What does it do with that? It gives you a mask around that point alone. Or if you give a set of points, a set of masks around those points alone. You could give a bounding box and it will give you the mask inside that bounding box. You could give a mask and it will refine the mask and give a label for that mask. Or you could just give text and it will find where the mask corresponding to that text is present in the image. As you can see, very diverse use cases can be used in many ways. How does the overall model look? The abstraction is you have to give a prompt and the image as input. So you have a prompt encoder and the image encoder. We will see the overall architecture very soon, but this is just the abstraction. These are then fed into a lightweight mask decoder, which finally gives you a mask as the output. Another contribution they have in this work is they also contribute a data set or a data engine as part of this work. This is called as SA1B or Segment Anything 1B, where B stands for a billion masks. Let's see more details of this approach. So from a task perspective, they wanted to define a task in such a way that if their model was trained on that task, it could then be used for many other tasks. And what is the task they chose? They chose prompted segmentation task, where given an image and a prompt, where the prompt could be a bounding box, could be a point inside the image or a set of points, or text or mask, the model returns a valid segmentation mask corresponding to your prompt. What do we mean by valid? Even when a prompt is ambiguous and could refer to multiple objects, a mask must be returned for at least one of the objects. That's what the paper calls valid. Okay, so here is a valid mask where you prompt using, say, a mask. In this particular case, you give the image and the valid mask is a refinement of the original mask given with a corresponding label. The model supports flexible prompts. As already mentioned, it can take prompts of different kinds, and it computes masks in amortized real time. What do we mean by amortized real time? Amortized real time is when you run a task over multiple trials and you get an average time complexity or a wall clock time of a particular number, is typically called amortized real time. For them, it was about 50 milliseconds per mask, which was fairly fast, and is also ambiguity aware, which means that even if you gave a mask that could refer to multiple objects in the image, it should pick at least one of the objects and return. For example, if there are multiple cats and you gave a text prompt as a cat in the image, it should mark any one cat in the image as the output. So their overall model had an image encoder, a flexible prompt encoder had to be, because they're dealing with prompts, and a lightweight fast mask decoder. So here was the overall pipeline. You take an image, send it through an image encoder and get an image embedding. So you convolve that with a mask if you end up giving a mask prompt, but if you give a point or a bounding box or a text prompt, you send it through a prompt encoder, and together they are fed into the mask decoder to get your final outputs of different masks. In this particular example, you can see that there is a mask here, there is a mask here and here, and then there is a mask for the full object as 3 different masks. Right? And obviously, if one of them was predicted as no object, you would not give that in the final output of the segmentation task. Now, what about specific components of the model? For the image encoder, they use a standard pre-trained vision transformer. For the prompt encoder, for box and point prompts, they are represented using positional encodings because they correspond to positions inside the image. Text prompts are encoded using a text encoder from a method called clip. We will see clip in the next module of lectures. And mask prompts are embedded using convolutions, as we saw on the previous slide. And finally, the mask decoder uses a lightweight transformer decoder block, which does 2 things. You can see that the input to the decoder are your image embedding itself and your output and prompt tokens. The output token is simply just one single token along with the prompt tokens that is fed in. There are 2 kinds of cross attention that the decoder does: an image to token attention and a token to image attention, both ways, cross modal both ways. And these are then, this token to image attention finally goes to an MLP, and that gives you the prediction of the mask at each pixel in the image. Okay. How is this done? How is this overall mask part done after the decoder? Recall your MaskFormer. Keep in mind that you have n mask embeddings, and then you have n class predictions, and then these n mask embeddings are compared with per pixel embeddings to get mask predictions, and then these 2 are combined to get your final mask outputs. So the segment anything or SAM uses a mask prediction strategy very close to the strategy of the MaskFormer. And that was about the task and the model itself. Now, what about the data engine component that we spoke about? So this is an interesting contribution of this work. To enable strong generalization to new data distributions, they realized that SAM needs to be trained on a very large and diverse set of masks. So what they proposed and developed, in fact, was a data engine that was built with a model in the loop dataset annotation strategy to create the segment anything 1 billion dataset, or the SA1B dataset, which has 1 billion masks. They achieved this in 3 simple stages. First stage, human annotators labeled masks using a browser-based interactive tool. SAM was trained using public segmentation datasets and these ground truth masks. Standard training using annotated data. This is how we would train any other model too, using annotated data. But then they went 2 steps forward. The second step, or the semi-automatic stage, is where they aimed at increasing the diversity of masks. High confidence masks were pre-labeled, and human annotators were asked to label any additional objects in the image, and SAM was retrained on this data. So when we say high confidence masks were pre-labeled, what do we mean? SAM's outputs on those images with high confidence were treated as masks, and human annotators were asked to provide additional masks that SAM may have missed out, and this data was further used to refine SAM itself. And finally, a third or a fully automatic stage where the model was prompted with a 32 cross 32 grid of points to completely generate masks that was used to create this 1 billion mask dataset, which eventually was used to train your SAM model. With this approach, SAM was evaluated on various different tasks. We will not get into discussing each of those tasks here, but we'll talk about a few of them very quickly. One interesting task was the single point valid mask evaluation task, where SAM is evaluated on segmenting an object from a single foreground point on 23 different datasets. This task is ill-posed because one point on an image could correspond to different objects, but they actually obtained significantly surprising and interesting results using this kind of an approach. So you point to one particular pixel and SAM would give you a mask around that particular pixel. So you can see the dot here and SAM gives you the mask around that particular dot. You can even have a set of pixels and SAM would draw masks around all of those pixels in this task. And you can see on this image some very impressive results that they obtained using SAM. Here is the performance of SAM on the single point valid mask evaluation in numbers, and they compared against an earlier such task and showed that they obtained significantly better numbers. Another interesting task was the zero shot text to mask. Why do we call it zero shot? Because the model was not explicitly trained on that particular label. Here is an example that you have a wheel and a wiper. The model was really not trained on these labels, but when prompted with text such as a beaver tooth grill or a wiper and wipers plus a point, the model gives fairly sharp masks around those areas of interest. Just to explain what's going on here, in the top left image, SAM is prompted with a text of a wheel and you can see that it actually draws a mask around the wheel. Similar for the top right where it's prompted with a beaver tooth grill. But now you see in the bottom two rows that when you say wiper, it actually doesn't get the wiper, but that gets one of these side windows which look like a triangle. But the moment you say wiper and also add a point as a prompt, that means you point a region where the wiper could be obtained, it starts getting the mask quite effectively. The same is the case when you go for wipers and wipers with a point prompt. Beyond this, they also evaluated on tasks such as generating object proposals and performing instance segmentation and showed significantly better results compared to baselines. One interesting task that they also show results on is zero shot edge detection. Edge detection is a low level task and they evaluate this on a dataset called the BSDS 500, where they prompt SAM with a 16 cross 16 regular grid of foreground points. That results in about 768 masks, 3 masks per point. They don't give more details in the paper on this. But it's interesting to see that using SAM, they're also able to solve low-level vision tasks like edge detection, where after the edge maps are predicted by SAM, they also do some post-processing by performing Sobel filtering and standard lightweight post-processing, including non-maximum suppression. More about this is also in the paper. As you can see, SAM had significant success in doing segmentation or also even tasks like zero shot segmentation, where the model was not even exposed to a particular label. More recently, in January of 2024, SAM was extended to grounded SAM, which is an open vocabulary detection and segmentation method. What does open vocabulary mean? Exactly was what we spoke so far, that the model can pretty much predict any label even if it has not been trained with those labels. This is what we typically call open vocabulary recognition, where the class labels or the vocabulary of class labels can be fairly open. Grounded SAM uses a method called grounding dyno, we'll talk about this soon, which is an open set object detector and combines it with a segment anything model. What is an open set object detector? Open set is a task in computer vision where, in addition to labeling bounding boxes with class labels, the model can also label a bounding box and say this is an unknown object. Being able to also classify unknowns and say that something is unknown to the model is typically called open set classification or open set recognition. Grounding dyno performs open set object detection and grounded SAM uses grounding dyno. We know that the annotation cost of detection is significantly lesser than segmentation because we only need rectangular bounding boxes, not very specific masks. And grounded SAM tries to employ this approach where it uses grounding dyno to get bounding boxes, and those bounding boxes are now fed into SAM to generate precise mask annotations. So you could look at this as a combination of SAM and grounding dyno which outputs bounding boxes, and they show that using such an approach they can achieve good performance on a wide range of vision tasks similar to SAM. Here is some background before we talk about grounded SAM. Let's first talk about grounding dyno. Grounding dyno, as we just mentioned, is an extension of dyno. Recall in the previous lecture we spoke about dyno as an object detector. Grounding dyno extends dyno by allowing text prompts as an additional input to the model. In addition to your standard image features that go into a detector, they also allow input of text, which could be a series of words or could be even a caption, which get converted to text embeddings, which are then given as input to the transformer model, and then they go through a couple of cross modality attention modules, very similar to what we saw with a few other methods where they do text image and image text attention, and finally they have model outputs with a few changes in the loss function. But the broad idea of grounding dyno is very similar to dyno, with just accommodating text input to be able to get your bounding box predictions. Right. Now coming to grounded SAM, they show that once you get the outputs of grounding dyno as bounding boxes and give that as input to SAM, you can do a lot of different things. Let's see a couple of applications that they show in their work at least. Here is one of them called RAM grounded SAM. An image caption model or an image tagging model, an example of that could be RAM, can be used to generate output results like captions or tags, which can then be fed as inputs to grounded SAM to generate precise box and mask for each instance. Please keep in mind that when we say we give these as inputs to grounded SAM, it's similar to giving input to grounding dyno, getting those bounding box outputs and then feeding that into SAM. Using this, they show that they get fairly interesting results for automatic dense image annotation, where you take an image and give a few text prompts as inputs to the image, prompts that the model may not have seen at all as class labels, and the model exactly points out in the image where they were located. This is a fairly impressive result. They also show that when you now combine this with generative models, with image generation models, you can now create a framework for a robust data synthesis factory. Having the capability of an image generation model, you can now control image manipulation, including image generation, and represent specific objects or remove certain regions in an image, so on and so forth. And this leads and has potential for generating synthetic images of different kinds, which could then be used for training data sets. Here are a few results where if grounded SAM is used for first of all detecting the mountain in the scene, and now changing that scene to introduce a concept art digital painting of an elven castle, it now places the castle on the same image by replacing the mountain. Once again, many impressive results in the paper. I'll highly recommend you to look at the paper for more of these results too. Just one more interesting application of grounded SAM is where they combined grounded SAM and another approach called OSX, which gets human body meshes from a given image, and they use this to obtain a promptable human detection and mesh recovery system. This realizes a promptable human motion analysis system itself. So given an image and a prompt to refer to a particular person, grounded SAM is first used to get a mask around a human in the particular scene, and then OSX is used to take that human mask and convert to a human mesh. So here you see a couple of examples where grounded SAM firstly is used to identify a person, and then OSX is used to convert to a mesh. What is the advantage of converting to a mesh? A mesh, remember, is like a 3D grid of that person. Now you can do a lot of things like analyze the motion of the person, analyze the joint angles, maybe even try to move the hand in a particular way to generate a different image, and all of that can be done once you get these 3D meshes. More about all of these can be found on a survey for semantic segmentation using vision transformers. I'll also recommend you to go through the Hugging Face link for semantic segmentation using transformers, and also the official GitHub page for Segment Anything. Just on a conclusive note for this series of lectures, one takeaway that you may have noticed is all of these different methods build upon transformers and modules inside the transformer architecture. They largely vary in how attention is used or how you adapt the transformer architecture for a given task. In fact, in many of these cases, we did not even speak about loss functions and how they are trained, because they all use standard detection loss functions or segmentation, where you use pixel level cross entropy or a differentiable IOU loss to train the model, and standard backpropagation across all of these methods and models. More about them, I'd encourage you to read the papers and these resources.